Hello everyone and welcome to this new video where we're going to talk about the long short-term memory and we will introduce the concept of controlling what information to remember and what to forget. Remember that in the RNN or the recurrent neural network we introduced the memory concept in the neural networks, but we faced the problem of the exploding or the vanishing gradient. So this LSTM helps us avoid this problem, and we're going to see the information flow in this specific architecture. So what is the long short-term memory? It's a special type of recurrent neural network designed to store information over long-term periods. The core idea is that it introduces a memory cell, as in the RNN, but it uses gates to control the information flow. So it learns when to remember, when to forget, and when to output the information. Unlike the RNNs, long short-term memory protect gradients during training, and we're going to see how to do that. Okay, so the architecture, it's as usual, we have the input, the hidden layer, this is all the where all the heavy lifting is done, and then the output. So if we unroll this, this is the middle part. So this is an LSTM layer. This is another one, because you can have more than one layer, obviously, especially for complex tasks. So if we just focus on one of these layers, we can see that it has 3 different gates, and we're going to see each one and what it does. So before we do that, we can see that there are several sigmoid and tanh activation functions. These are not random. We specifically use these two in this architecture because the sigmoid function, the output should be between 0 and 1. We will use it to determine the percentage of the memory we want to keep or forget. So if the result after the activation is 0.95, so we will either keep or forget 95% of the information. And in the tanh, it's the value should be between -1 and 1. Okay, so starting this top line represents the long-term memory, and this one here represents the short-term memory. We can notice that especially in the long term memory that there are no weights and no biases that are directly affecting the values here. So we will not obviously have the exploding or the vanishing gradient problem. We just have a multiplication, this is multiplication, and a summation, this is a plus. So this is the previous long-term memory or previous value, and this is also the previous short-term memory or previous value, and this is the input from our data. And the first layer, these should be 0 because if this is our first iteration in the first layer, in the first step, obviously we have nothing to remember because we're still fresh, so these should be 0 here and 0 here. Not like the weights and biases that starts random and then gets updated. Okay, so let's start by looking at this forget gate. So the objective of this gate is to remember or decide how much of the long-term memory we will memorize. So how do we do that? So we said that we have the previous long and short-term memory or values. So when we introduce the new input from our dataset, we would multiply it by the weight, a random weight, and add it to the previous short term multiplied also by a weight. These two weights do not have to be the same values. And then, of course, we add them to the bias. And next we do the activation. Since it's sigmoid, it will be between 0 and 1. So let's say, for example, after multiplying the input by the weight plus the previous hidden or the previous short-term memory multiplied also by weight, and then sum them all up and add the bias to the activation, we get 0.5. We get this 0.5 and multiply it by the previous long-term memory. So we're basically saying that we will keep half of the long-term memory that we have. So let's say this one was 10. The value of the previous long-term memory is 10. So we will only keep 5. This is the objective of the forget gate. Now, moving on to the input gate. The objective is to decide what new information to store. So we will get new information here, decide the percentage that we want to keep, and then add it to the long-term memory. Remember, in our example, we said 10, so it was 5 here because we only kept 50%. So how to do that? We get the input. This is the information flow. The input, let's start by this one. Multiplied by the weight plus the bias, make the activation function. We get an output between -1 and 1. And also get, let's change the color. The input again goes through this part, gets multiplied by the weight plus the bias, goes through the activation function, which would be between 0 and 1 because it's a sigmoid, as we said, and then we multiply these two by each other. So let's say this one was 3, so we added the value 3 as new information, and we decided to store, let's say this output was 0.2. So we decided to keep the fifth of this 3, which is 3 multiplied by 0.2, and add it to 5. So whatever this result here would be added to 5. Let's say it was 2, for example. So 5 plus 2, it's 7. So for the input gate, after doing all the work, we get this value that we're now going to pass to the output gate. This is what we said. This is the potential long-term memory, and this is the percentage that we will remember from it. Okay, so now for the output gate, we will update the short-term memory or get the output value. So we will understand more with this demonstration. The information flow, again, this is the input from the dataset, multiplied by weight plus bias, goes through the activation function. So it should be a percentage. Again, it's a sigmoid. Let's say it's 75, 0.75 or 75%. So from this input, we get 75%, which is like what is the percentage that we decide to keep. And we said that we have the value 7 from all of this gates output. It goes here. So it goes both ways. Goes 7 here for the next layer. So if we're starting another layer, we will start with 7, not 0. And the other flow, the 7 would go multiplied, of course, by the weight plus the bias, do the activation. Let's say it was between -1 and 1, so it's 0.5. Multiply the 0.5 by the 75%, and that value that we got is the output of our, let's call it y. It's the output of all of our long short-term memory. So I realize I made the mistake here. This can't be 3. It should be a value between -1 and 1. Okay, so we have to add an information that the weights plus biases used here are not the same. Weights and biases here, different from these here, different, so they're not the same. But they are all the same when we go to another layer. So let's say we multiply this input by 3 plus 2. 3 as weight, 2 and the bias. Different weights and biases here. Different weights and biases here for this previous short-term memory, which is also the y. So next layer we will start by y. The same as we will start by the 7. So weights and biases are different. They are all different across all of these cells. And then we will use them again in the next layer. So yeah, that's it for the long short-term memory. If we want to see an example to better understand what we're saying, so this is not a numerical example. We will make a separate video about that. So this is, let's say, this is a stock price. This is the time. This is the price. Let's say the stock price started at, let's say this is 5. And of course, by time it will go up, sometimes down, up, down. Let's say this is the crash of 2008. So if we are here and we are interested at predicting price, of course the previous price, let's say of this year, is more important than the price of, let's say, of the year 1990. This would have more weight, more importance to the prediction and the influence of the next price. That's why we would give this a small percentage, or ideally the model would give it a small percentage of how much you want to keep. so we will almost forget the price in this year. So in summary, what the LSTM does, it will read the input from here. We will decide what to forget, and then decide what we will add in this part. Then we multiply them. We will add it to the memory cell, long-term memory. And then we will also decide how much we should keep from it. And finally, have the output that we're interested in. All of this happens for every time step in the sequence. So for the next iteration, we will use this output as the input here, and this output as the input here, and we will do the same steps. So yeah, the LSTM are pretty easy. So please like and subscribe.